Let's get the sun back out. What was the story that video said about Jupiter? Has Jupiter always been where it is? Or did it used to be?
Closer.
Yeah, it used to be there, it came closer, and then it went back. Yeah. Do you remember why it went back? Yeah, because Saturn kind of pulled it back and kind of stabilized it out there. That is so cool. And then, so kind of related to that is this idea of what we call the condensation theory. The condensation theory. If water condenses, what does water do? It can fall after condenses, but what's like physical phases is it going?
Freezing.
Sort of. If it condenses, it's going from a gas to a liquid. Yeah, that's condensation. So this idea of sometimes called the solar nebula theory, I think, condensation theory, simply means you can kind of see it here. These go from 1 to 2 to 3 to 4 to 5. 5 being kind of, you see the sun there, and you see the planets orbiting the sun, okay? And 1 being actually what we call a solar, I've used the word before, nebula. It's on the slide coming up. So this is actually the kind of the gas stuff that made the sun and the planets, okay? So the condensation part is that it kind of collects from gas to kind of a liquid or a solid. So the first part, you need a solar nebula, that's number 1. The word is contracting there, begins contracting. What's contracting? Getting small, yeah, kind of contracting, yep. And so actually, our sun is a star, right? And the way that stars need to create their energy and shine is they have to have in their core, in the center of the star, the center of our sun needs to be very hot and high pressure. So that's the contraction part. So the particles get larger and the solar nebula rotates and flattens out. And I kind of liken this to here in Iowa, right? Some snows are better at building snowmen than others, or snowballs than others. But if you get a nice snow that's of the right consistency, you can go ahead and build a snowball. And to me, that kind of is what happened with the planets. They kind of, and we pick on, if I'll go clear out here, we pick on Pluto because he or she did not clear their orbit, okay? So these other planets cleared their orbits. The word is planetesimal. I just think that's adorable. Of course, kind of at the root of planetesimal is planets. Planetesimal is like a baby planet. So that would be like a small snowball that's got stuff in its area to try to get bigger and bigger. Okay. So the planetesimals are forming in their track, and what's a prototype? What does a prototype mean?
It's like if you like make something and it's like just a prototype and it's like the starting product that you're like testing to make sure that
it's the starting product. Yep, and it's still got time to develop. Yeah, very good. Exactly. So proto-sun, prototype. Protoplanets cleared their orbits. So protoplanets. So we went from planetesimal to protoplanets. They kind of are growing. They cleared their orbits. And that's where, like I said, Pluto failed. Ultimately, all stars and our sun begins, how it creates energy is this word fusion. The sun creates energy by fusion. Okay. And how long ago did that happen? And I put it up on the slide. It happened about 4.5. What does BYA mean? Billion years ago. Exactly. 4.5 billion years ago. Sometimes we'll round that to 5 billion years. So we got about another 5 billion years, and then our sun is actually going to swell. And it's not ever going to blow up. The sun's never going to blow up, but it's going to swell and kind of end its life in what we call a white dwarf. So notice that actually when you guys did your solar system in your pocket the other day, one of the things I had that you put past Neptune, I think I had you put Pluto / Kuiper belt. So there's the Kuiper belt. And then I think we've talked a little bit about it. We talked about it on Friday. We have kind of, these are where the comets are, Pluto is and comets are. And we have something called the Oort cloud, which is even bigger than the Kuiper belt. The Kuiper belt kind of lies in the plane of the ecliptic. So this condensation theory, which is kind of parts 1 through 5, has to make sense because we want things to make sense with our observations. And the observations specifically are that the orbit and rotations of the planets are, what direction does the Earth orbit the Sun in? So clockwise or counterclockwise? Counterclockwise? It is counterclockwise, yeah. It's all about counterclockwise. So all the planets orbit counterclockwise, and which 2 planets spin backwards? Uranus and Venus. Yep, they spin backwards. Yep, you're right. You got it. Very good. So we'll kind of hold that thought. We'll be kind of return to that. Here's a little bit of history about where we are today in astronomy, the science of astronomy. Now, this is before the method of scientific study, the method of scientific reasoning really came about. Science is such a pretty thing. Actually, science to me came out of philosophy. And these are some philosophers, okay? So, let's see, if I wanna, I think this will work. So that's been the Sun, but actually I'm gonna go ahead and now put the Earth there as the center of tension. And for a long time, folks thought that actually everything orbits the Earth. Like, oh, how does that work? Well, today it does not quite make sense. You're like, stars orbit the Earth, really. But back then it was like, well, why not? Because we're all that. Sometimes I think we still think we're all that. Well, we are kind of all that, but I don't know. We're not all that bad. Okay, so if you think about this, actually this is called an Earth-centered or geocentric model of the universe. So you're like, all right, well, the Sun orbits the Earth, the Moon orbits the Earth, and it looks like the stars orbit the Earth. Makes sense. And you got to give them credit because they are working with what they know. Yeah, this is called the Earth-centered or geocentric, here's those words I just said. Earth-centered or geocentric model of the universe. And who am I to diss anybody for thinking that? So, and then philosophy and religion, I would think still have a connection, and they did at the time. So we're all that, and we're perfect. And one of the things that's perfect, as shaped as perfect, is a circle. And spheres and circles are perfect. Ovals are not perfect, and here in a minute you're going to see that that was kind of the barrier to kind of breaking out of this model. So, keep that in mind. So one of the things to breaking out of this model of the geocentric, having the Earth at the center, actually was this idea. Now what you're looking at, you can hopefully kind of see some background stars. That orange thing actually is Mars. And Mars, along with the other planets, generally, the word planet means wanderer in Latin, and it doesn't quite work because you're thinking wanderer, it's kind of like random. Not really, but the planets do actually go eastward. I know they go eastward from June. This is Mars, it's background side of Mars. June, okay, and then this is what we call backwards motion, but this is the eastward motion. So mostly what you see from June to July and from September to November, that's what all the planets do. Okay? So like I said, the word planet means wanderer. And it's not random because, to put it another way, it has a narrow path that the planets stay on. And that path is actually what we call the plane, it marks the ecliptic in the sky. So, but now there's this backward motion, and on this slide, the backward motion, I have a video to kind of show you in a minute. The backward motion would be from July to August to September. This is the backward motion, okay? And this is what we call retrograde. Retrograde, retro, backwards, apparent retrograde motion. And then it goes normal motion, what we call actually kind of direct motion, back from September to November. So, and we're going to see an example where a thinker back then, Ptolemy, was kind of the last gasp of having the Earth at the center of everything. The planets orbit the Earth, the sun orbits the Earth, the stars orbit the Earth. We're going to see actually he came up with kind of a clever way to explain this backward motion. But otherwise, this backward motion, this retrograde motion, was something that was kind of difficult to explain. So here's Ptolemy. I kind of think he's the last gasp at geo meaning Earth, centric meaning center. So geocentric model. He's the last gasp at it. Okay? So he's kind of extravagant, and it looks like this. So geocentric means Earth at the center. This gray thing right here that you see would be, could be the orbit of Mars. You kind of see the main orbit of Mars, okay? Mars orbiting the Earth. And then you see it kind of do these loop-de-loop, which are called epicenter, or around an epicenter, it does a loop. So Mars would go, and I have a pointer up here. Mars would go like this, and then it would go loop-de-loop, and here's where you'd get retrograde motion. And then it would be direct, retrograde, loop-de-loop, okay, like that, loop-de-loop. So that's one way. Actually, one of the hallmarks, oh, sorry, the word is planets right there, of the planets. One of the hallmarks of a good solid hypothesis, let alone a theory, is one that is not too complicated, and these little loop-de-loops make it sort of kind of complicated. You're like playing Twister, in fact, observations. Okay, so now what we know today is what Copernicus introduces. Actually, again, he wasn't the first one to introduce it, but he kind of was a turning point. And around Copernicus's time, they were starting to kind of work with and develop the method of scientific reasoning. So helio means sun, centric means center. So beginning with Copernicus, we're back with the sun in the center again. Heliocentric model of our universe. And so actually, with that in mind, he was able to go ahead and lay out, so we have the sun. What's the next one? Cute little circle again. And then after Mercury comes Venus, and then Earth, and then Mars. And then what comes between Mars and Jupiter? An asteroid belt, and then Jupiter, Saturn, Uranus, Neptune, and then Pluto. And Pluto is in, starts letter K, what we call Kuiper belt. Yep, Pluto's in the Kuiper belt. You got it. So Copernicus obviously didn't know about, actually, I want to say, I don't know if he knew about Saturn. He didn't know about Uranus, Neptune, Pluto, and Kuiper belt. He did not know. Okay. But we're going to kind of revisit why, if you put the sun in the center, why you can explain that retrograde motion of the planets. So I'm going to play this video for you right here. Yeah, it's part of this video. So the heliocentric model, I'll try to show you why this is, and it's actually related to this figure, can explain why Mars looks like it goes backwards. So let's check out this video. I have a few planets, I have a few more scientists to kind of throw at you. Beginning with Copernicus, at least Copernicus now put the sun in the center. The planets orbiting the sun. Oh yeah, and I'm going to kind of, here in a minute, talk about Kepler, and that is one of Kepler's laws. That being that the closer you are to the sun, the faster you move in your orbit. You'd be like, well, yeah, because you have a smaller circle to complete, or actually it's an ellipse, but a smaller orbit. But no, actually, as it turns out, for instance, we're closer to the sun than the Earth, and so actually we'll go faster in our orbit than Mars will. We're closer to the sun than Mars, excuse me. Earth is closer to the sun than Mars, so we actually move faster in our orbit than Mars.
That feels like the gravitational pull.
Yeah, definitely it's a gravity thing. We sense the gravity more strongly than Mars does, and that has more of a swing than it. Definitely. Do you guys remember how long did it say that it takes to, how long do we catch up with Mars again?
2 years.
Yeah, about every 2 years. And then kind of, it's not a coincidence. It's definitely related that when NASA or ESA, which would be the European Space Agency, when they're planning to send something to Mars, which Mars is a very busy place, they kind of time that to those every 2 year options. Okay, so we see apparent retrograde motion. The word is pass when we pass a planet in its orbit. Another thing, kind of unrelated to this idea of seeing a planet move backwards against the background stars, is this idea that you guys told me the order of the planets was Mercury, Venus, and Earth. So actually, Mercury and Venus have a special place in that they are inner planets relative to the Earth, Mercury and Venus. And for that reason, actually, and if we even take this, okay, so I'm the Earth, and let's go ahead and line up Venus and Mercury. Do you see where I couldn't see them if they're kind of in line with the sun, right? Because the sun scatters the light in our skies and all that. Now, a cool thing can happen when that happens. Have you ever heard of the word transit? So back in, was it 2006? Was it that long ago? I don't know. But you can actually see the planets, Mercury and Venus, go in front of the sun if they're lined up just right. They won't eclipse the sun, but if you have special gear, you can block out the brightness of the sun, and you can actually see Mercury and Venus going in front of the sun. Okay, so a few more names. We begin with Copernicus. He's kind of a turning point. Then we go to Brahe, and this is Tycho Brahe. He did not have a telescope yet, but he was a kind of a nobleman, had some money, and he got some awesome, impeccable data, like some very important data to kind of show how these planets wandered. So the word is planetary positions. And the word is predict there. So I'm pretty sure Brahe was a geocentric, he was an earth-centered sort of dude. I'm pretty sure. So he could not, so he was going against Copernicus. He could not resolve his observations based upon even Ptolemy's cute little epicenter things. Okay, so what Brahe did was hire, and I like to think of Brahe as kind of the nobleman having all this money, and I like to think of Kepler as not having much money. And I don't even know if Kepler got all the credit that he should have. But Kepler took Brahe's observations and actually came up with 3 laws of how planets orbit the sun, including the one, like I said before, that the farther you are from the sun, the slower you move in your orbit. So there's Tycho Brahe, there's Johann Kepler. Okay. So the word is circular there, and again, there was you'll see this in astronomy, kind of one of the first budding sciences to come out. There was this connection between science, which was kind of budding, and religion, and the whole perfection of our planet. And I think our planet's great, but I don't think it's perfect. I think I'm great, but I don't know. I know I'm not perfect. Okay. So I mentioned the perfect shape a little bit ago was the sphere and the circle. And so Kepler first tried to do kind of like what Copernicus did with the sun in the center and having the planets orbit in circles, and that didn't work. So if you take a circle and kind of elongate it, you get something I call an oval, and the fancy name for an oval is an ellipse. Okay. Now it's not exactly where you take a circle and kind of squatten it out. There's some characteristics to get an ellipse from a circle. But that's kind of what it is, an oval. So here's one where he's famous for saying, Kepler, who pored over the data that was left by Brahe, said, you know, I could have, if I just would ignore this error I'm seeing, then I could have force fit the shape of the orbits into circles instead of what now we know them to be ellipses. But as a good scientist, he didn't want to do that. Okay, you take your data and you're proud of it. So this looks like an oval, hopefully. Okay, this red would be an ellipse. Like I said, there are some important features of an ellipse, and this is the shape of the orbits of the planets. They have belly buttons. Can you see kind of the two green tabs there? They're not belly buttons, they're called foci. They're sort of spokes. Okay. So one of the things about those belly buttons, where those green things are, well, a few things is you can see hopefully by the person with the pencil drawing this oval or this ellipse, wherever you are on that red line, that ellipse, the distance between the two foci, actually, if you add them together, it's going to be correct. That's what you're going to get. It looks like a little spiral graph. But that's what you get by limiting it that way. One of the things then, important to this idea of the shape of the planets orbiting the sun, is that the sun is off-centered. So the sun is at one of those two foci, one of those two belly buttons. Okay? So it's a little exaggerated here, but the blue line could be the path of any planet. And since it's off-centered, sometimes planets are closest to the sun, we call perihelion. Peri means close, helion means sun. And sometimes, if the planet is clear over here, it's furthest from the sun. Okay, this distance right here, okay, this is a lot farther. The farthest it's going to be than this distance is close. Perihelion, over here, the farthest that a planet can get from the sun we call aphelion. Okay. So Kepler's first law says it's not about circles, it's about, I'll call them ovals, more fancy actually, you should know are ellipses. Okay? The other thing actually has to do with perihelion and aphelion, and each individual planet, now this isn't relative to other planets, but it will move, and I can almost feel this in a, let's see, we're actually, during our summer solstice, we are actually farthest from the sun. We're closest to the sun. We're at perihelion about January. It's kind of come and gone. January 4th or something like that. Okay. So I am the Earth. Of course, that's the sun. Planets, and it's a gravity thing again. Planets will move slowest when they're far away. This is the aphelion, and fastest when they're close to it. So here we go. So I'm slow out here, and then I'm faster, 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 fastest at perihelion, slowest at aphelion. That's the second one. All the planets do that. And all the planets have kind of this common elliptical shape, and the sun is the foci. Oh, equal times. So that's the gist of it. Now the same law can be said another way. So if I'm going slow out here, okay, so I'm going to go slow out here. So if I go from this point to this point, which is actually over there, July 5th, and take that area, which is pretty, take this chord, or this segment, which is pretty long, because, well, no, pretty short because it's really slow, and then go back to there, I'll get a piece of pie that has a certain area. If I go ahead in the same time segment, go over here, and I'm moving fast, so I'm going to have a big segment, and it's kind of a fat segment, coming back, but it's not as deep. This area is equal to that area. Bottom line, if I ever ask you Kepler's second law, you can say it moves fastest when it's close to the sun at perihelion, and slowest when it's away from as farthest from the sun. Okay. Faster, nearer. Sorry, two words. Okay. Well, his third law is the most elusive. But I guess if you think about it, we've already kind of talked about, so here it is, distant, slower. We've already talked about this one. But it looks real number oriented and just kind of drives me nuts. His third law then kind of switches gears, and we're not talking about individual planets, we're talking about relative planets. specifically relative to their distance from the sun. So I'll put it in form of a question. Which of these, we'll go out here to our gas giants. Which gas giant, Jupiter or Neptune, goes fastest in its orbit? How many people think it's Jupiter goes fastest? How many people think it's Neptune goes fastest? You're right, Jupiter. Yeah, Jupiter goes fastest. Yeah, that's his third law. All right. Okay. I guess I should go back here. One of the things, a term that's important in astronomy, I'm going to switch gears to the sun for a little bit, is this idea of distances. I don't know, did I ever talk about light year? Maybe, I feel like I did. Light year is a distance that it will take light 1 year to get from point A to point B. Light years are way far away. Closer distance in our solar system, I think I talked about this maybe when we did your models the other day, is an AU, capital A, capital U. And like the slide says, that's the average distance between the Earth and the Sun. Now we know why they have to use an average, because sometimes the Earth is closer to the Sun, apparently, and sometimes it's farther from the Sun, apparently. And do you remember, when is the Sun closest to this? When is the Earth closest to the Sun? January, yeah. January 4th or so. It's closest to the Sun, but it's cold in January. So it must be the fact that the Earth's axis of rotation is tilted. So here we are. Here we were in December, clockwise. So here we are in January. Okay. So this is perihelion and Earth's axis of rotation. Daylight hours are less, and the sun's rays are less direct. We've got a few minutes. We're going to take a look at the sun, people. I got sun binoculars, like solar binoculars, regular binoculars, but you can look at the sun safely. This will make more sense when we talk about the sun. But have you heard like the sun doing like solar flares and stuff like that? Probably. Solar flares can play havoc with communications and stuff. And those are times when you can take your solar binoculars out and you can see things. But the sun's been very quiet lately for the last, I want to say 5-6 months, very quiet. Sometimes, you have cool solar binoculars and there's nothing to see. But I'm proud to say that the sun is ramping up. So hopefully, we'll get solar binoculars. So the sun is just a regular star. So as we kind of talk about what's going on with the sun, think about, wow, what's going on with other stars. You can kind of see these three colors. The colors are different layers of the sun. The inside layer, I guess you wouldn't call it a layer, but the center of the sun kind of looks like a Tootsie Roll Pop, is what we call the core. Okay, so the core is where the energy has been created. And I already mentioned the word fusion. Let's see, I didn't, but I'll add it up there. What's being described here with hydrogen is being fused, well, the word fusion, fused into hydrogen plus hydrogen goes to form helium. So for a lot of times people know their elements. This is the symbol for a hydrogen atom. This is the symbol for another hydrogen atom. This is what we do in chemistry to say goes to form. It's going to have some sort of chemical reaction. And what's this the symbol for? Helium, yeah, goes to form helium. And a lot of energy. And sometimes we just put E for energy. So anyway, that's what's happening in the core of our sun and stars. But it has to be hot, very hot, and it has to be high pressure, or it's not going to work. So those are conditions that have to kind of come into play before a sun turns on or a star turns on. Oh, it is up there, nuclear fusion. I guess I'd probably put that in. Three things in the center of the star, the sun. Three interior zones. We have the core, we have the radiation, or sometimes I go radiation, radiative zone, and then we have the convection zone. So those three areas. So the core, radiative or radiation zone, and the convective zone starts going. Let me double check what's next. I think we'll go ahead and stop there because I'm gonna take a running. I want to bring a thing to kind of show you a little bit about convection. So we'll start here hopefully on Wednesday. And the cool thing about y'all's class is I'm not trying to keep you in sync with another class. So you will have your test a week from Thursday, and however far we get, that's however far I put on the test. But this Thursday, I think we're gonna have a telescope. Be careful out there, everybody.